Hello everyone, I hope you are doing well. So in today's video, we'll be going through the 2023 Physics Exam Short Answer Questions Part 1, where we'll be going through questions 1 to 9. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. So question 1. Some physics students are conducting an experiment investigating both electrostatic and gravitational forces. They suspend two equally charged balls, each of mass 4 grams, from light non-conducting strings suspended from a low ceiling. The charged balls repel each other with a string at an angle of 60 degrees as shown in figure 1. There are 4 forces acting on the ball: tension, gravitational force, electrostatic force. On figure 1, using the labels T, F, G, F, E, draw each of the following forces acting on each of the charged balls. Okay, now the easiest one is draw the force of gravity. Basically, the force of gravity is always acting down. So we're going to basically draw that first. I'm just going to duplicate this and put it right there. So both will have a force of gravity. They will also have a tension force that will be on the rope, basically like this. Tension. Done. And of course they have an electrostatic force like they said, so that will be making them repel. Basically, so repel. And that is it, and that's Fe. That's it. Are we missing anything? Yep. On figure. Beautiful. Next question. Show that the tension T in each string is this. Use G as that. Show you working out. Basically, this is easy. I will just form pretty much a triangle. I'll just form a right angle triangle. And basically do Pythagoras theorem in these cases, because that'll make my life so much easier. For example, I'm going to take that tension, which goes like this, here. Basically, the length of it, I'm going to put it over here. I'm also going to take this force of gravity and I'm going to put it down here. And I'm also going to take that force of electrical, I'm going to put it over here. Don't worry about the directions. All we want is the magnitude. Basically, I know this angle here is 30. I mean, is it 30? Wait, was it 60? But halfway through 60. So if I break it down, it's halfway. So it's 60, actually. 30 degrees, basically. So it's 60, so this has to be 30 degrees. Yep. And of course, this is your force of gravity, that length. So this is your force of gravity. Now, basically, I know what my force of gravity. I know the mass, I know G. Basically, I know that. So I want to use that to find the tension. I know this is my opposite. This is my hypotenuse, and I know the adjacent. So because I want to find the hypotenuse, and I know the adjacent, I'm going to use cosine, basically. Cosine, 30 degrees, is adjacent, which in this case is your force of gravity, which, of course, basically it's mg. What's our mass? 4 grams. What's 4? So 4 divided by 1,000 to make sure it's in kilograms is basically 0.004 times 9.8. Make sure it's in force of gravity over your tension. Hence, your tension force is basically 0.004 times 9.8, all being divided by cosine 30. Alright, so that's going to give me 0.045, which is basically this over here. So my tension, hence, is 4.5 times 10 to the negative 2 newtons. Done. Calculate the magnitude of the electrostatic force Fe. Basically just using the same thing. Let me just copy and duplicate this whole thing. But now, in this case, I don't want to find this tension. I want to find O, which is our opposite, because that's where my electrostatic force was, Fe. So basically using the same thing. So this is my opposite. I know my opposite and adjacent. I want to use those. That's tan. So tan 30 is basically opposite, which is Fe, over Fg. Fg, remember Fg is just basically your mass times your G value. So which is 0.004 times 9.8. Am I making anything? So 10. Yep. So Fe is basically 0.004 times 9.8 tan 30. So what's that? Tan 30. That's going to give me how many? So two significant figures. Basically 2.3 times 10 to the power of, so 1, 2, -2, basically. That's it. Beautiful. Next question. Question 2. Phobos is a small moon in a circular orbit around Mars at an altitude of 6,000 kilometers above the surface of Mars. The gravitational field strength of Mars at surface is this. The radius of Mars is this. Show that the gravitational field 6,000 kilometers above the surface of Mars is 0.48. So basically what we're trying to show is, say this is your Mars, and this here is your Phobos, basically your moon. So we basically know the distance or the altitude. So the altitude, remember, it's the center to the surface of Mars. Is what was it? 600 kilometers. So 6,000 kilometers. And we also know, so yep, above the surface of Mars, the gravitational field strength of Mars is that. And the surface, the radius of Mars is that. Okay, basically, I would say, this is how I would do this question, basically, if I wanna. I would consider this to be, so wait, so that's 6,000 kilometers above the surface of Mars. The gravitational field strength at Mars at its surface. So at the surface here, G is what? G is 3.72 newtons per kilogram, basically. And where, of course, from the center, it's basically your radius, which is 3,390 kilometers. Beautiful. Show that the gravitational field strength at 6,000 kilometers. Beautiful. This is easy now. So now I get visually what we're doing. What we want to do basically is, think of it like this. If I have a value of G at some point on the planet, like for example, I know the point of radius, I know the radius and the value of G for it, and I want to find basically another point of G where I'm giving the radius also for it. There's this formula that I would say write it in your summary sheet. Basically, it says, I'm going to have a look at the summary. It's G1, yep, over G2 equals basically R2 over R1 squared. So basically G1 and R1 are basically your conditions that were first given. So like R1, we're given that on the surface of Mars, basically on the surface of Mars, which is pretty much 3,390 kilometers. So times 10 to the power of 3 to make it meters. That's your radius. And we know our G value for that at the surface is what? They told us it was 3.72. R2 is the new point. And basically it's the at this point, which is both adding this and that to make sure, you remember it has to be from the center. So, so it's going to be 6,000 kilometers plus 3,390 times 10 to the power of 3. And we're going to try to calculate G2, basically. So, G1 is 3.72. G2 is what we're trying to find. There's many ways to do it, but I think this is the most easiest. R2, is 6,000 times 10 to the power of 3 plus 3,390 times 10 to the power of 3 over R1, your radius 1, which is 3,390 times 10 to the power of 3, all being squared, basically. And so you can calculate G2 using algebra. That's how I would do it. There's many ways. For example, you could have basically used also G equals GMR squared, so GMR squared, to calculate the mass of the Mars, and then basically do it for that new point. But I think this is just a better way. So I'm putting this on my calculator, basically. So write it now. So basically it's 3.72 G2 is going to be equal to what? So let me do that. It's a lot. So 6,000 times 10 to the power of 3, 3,390 times 10 to the power of 3, 3390 times 10 to the power 3. All squared. That gives me 7.67. And basically, so G is what? 3.72 divided by that. So, yep. So my G2 basically is 0.484. Which is basically this over here. Done. Calculate the orbital period of Phobos. Give your answer in seconds. Now, when I think of straight-away period, the most common formula that comes is Kepler's law. But we still haven't calculated the mass of Mars. For Kepler's law, we need the mass of Mars. So that's a useless kind of thing to use. Luckily, we're given the value of G at that point of Phobos. So what I can do is, I'm looking at my summary sheet. What formula can I use? I know the acceleration at the point of Phobos is equal to 4 pi squared r over t squared, basically. So, I know A at that point is 0.48, basically. And that's equal to 4 pi squared. The radius is what we calculated, which was 6,000 times 10 to the power of 3 plus 3390 times 10 to the power of 3 over t squared, where basically t is the square root of what? So let me just calculate down. So what's 4 pi squared 10 to the power 3 plus 3390 10 to the power 3, 0.48, and take basically the square. So this is your. So we're taking the square root of 772,296,544.4, and that's gonna give me. So square root of that. That gives me 2.27790 basically. And so making that into how many, like 3 significant figures, basically that's 2.78 times 10 to the power of 1, 2, 3, 4. To the power 4 seconds. That's it. That's your period. Is that right? 1, 2, 3, 4. Yep. Phobos is very slowly getting closer to Mars as it orbits. So basically its radius is decreasing. Your orbital radius. Will the orbital period of Phobos become shorter, stay the same, or become longer as it orbits closer to Mars? Okay, easy. We know the way you explain this by using Kepler's law. So basically, let's just write what Kepler's law, and let's make the formula for period basically. So 4 pi squared gm. So t is basically the square root of 4 pi squared r cubed over gm, where basically now that period is pretty much proportional to the square root of r cubed. Basically, that's all we're going to need. This is our formula that we're going to be using to explain what happened. Well, let's look at this. We know as the radius we said was decreasing, the period will also decrease. So it will become shorter. Easy, we answered that. And now we just basically explain by using these here. So for example, this is how I would explain it. So I'm going to say, so as from t equals, basically copy this. I mean, basically as from this here. As from that. T is proportional. I mean, just copy this as we know that this is proportional to that. So, as Phobos gets closer to Mars, R decreases. Hence, T decreases. Basically, and that's it. As for that, we've shown, so if as Phobos gets closer to Mars, R decreases and hence T decreases. Basically, that's all you need, 2 marks. Wow. Question 3. 2 long straight current carrying wires, P and Q, are parallel as shown in figure 2a. The current in the wires is the same magnitude and the opposite direction. So figure 2b shows the wires as viewed from the above. Alright. So on figure 2b, sketch the magnetic field lines around the wires showing the direction of the magnetic field lines using at least 5 field lines. Okay, let's have a look at these. So basically we're given, why is that, there's current passing through them. So basically there is going to be a magnetic field that's produced because current carrying wires produce magnetic fields. And the way you will determine it is using your right hand grip rule. So you can see that P is actually into the page. So make sure your thumb's into the page and you should see that there will be basically, let me draw it nicer. So let me draw it like that. Basically, it will look like this. So there will be, so if I'm putting my hand into the page, there's going to be a, basically, current is going to move like this, basically. Done. Basically, that's how current's going to pretty much move. And so what I'm going to do, or should have, duplicated this here, but I'm going to rub these magnetic field lines because they're going to be different likely. Alright, that's too much work now. Alright, so what about the other one? Make sure you use the right hand grip, but it's going to be coming out the page. So it will go this way, anti-clockwise basically. So let me write it now. That's it. And so basically these here are kind of coming, can you see how both are indicating they are coming, down? So I feel like there's going to be an addition of vectors or magnetic field lines, and there's going to be a bigger magnetic field. Like a stronger magnetic field that's going to go down the page. So for example, what I'm saying here is like, what I'm looking at is basically, as both go down, so as both go down, there's going to be an addition of a downwards vector or downwards field line that's going to basically be downwards, looks like that. I mean, you don't need to draw that. I'll draw like that's, I think that's 3 field lines to be honest. 5 field lines, but you can draw again more circles. You don't need to do that straight line. So basically, but yeah, I think that's nice. Do the 2 wires P and Q attract or repel each other? Explain your answer. Well, this is how I would do this. Okay, so imagine, okay, basically we have 2 lines here. What I'm going to do is I'm going to look at one of these lines, like for example, Q in this case, and I'm going to make sure it's the one that's producing the field. For example, using my right hand grip rule again, imagine holding that wire, and you would realize that the lines, your field lines, should be coming out the page here. Make Q pretty much, and then of course they're going to be coming into, but we don't need to care about those. So we can see that basically that the field lines are coming out the page. So I'm going to just draw some basic here that Q is producing. And so what I'm going to do is I'm going to copy that, duplicate, bring it right here. So imagine that Q is pretty much producing these field lines, they're producing this field, and P is basically going to experience a fault because you remember it's a current carrying wire in a magnetic field. So there's going to be a force produced, and we're going to use our right hand slap rule in this case and determine how the force pretty much reacts. So make sure your thumb's going down, your finger's going to be out the page, and you realize that there's going to be a left force acting on it. So there's going to be a force on P. It's going to be this way, basically. So let me just take these out. I don't need to take that, so let me take those, and I'll nicely draw it now here. So this one's already not attracting it, but it's repelling. And you can do the same for the other one. Let's also do the same for the other one. I'm going to take these, because if they are the same, I could really use them. So for example, what about the next one? So imagine, okay, now P, so imagine P in this case is creating that field. So you're going to use your right hand grip rule, but your thumb's going to be downwards, and you'll realize that they're still coming out. So in this direction, they're going to be coming out basically. So it's the same thing. And so again, using your right hand grip rule, your right hand slap rule, your thumb's going to go up on Q because that's where the current direction. Your fingers are going to be out the page, and you realize that there's going to be a force basically to the right. And so you can see that they will repel each other, basically. You can see that these forces basically repel each other. Easy. And we'll explain how we did that. So, repel, basically. And let's do that. So, okay, let me a little bit zoom in. Okay. Basically using the field from Q. So let's use this Q. So using the field that Q produces from the right hand grip rule the field is coming out the page. So it's coming out the page and act on the current carrying wire P. And so what does this do? Using the right hand slap rule now, and slap rule, the force, so if the force was to the left, was to the left on P. Doing the same on Q, why Q like that? On Q, the force was to the right. Hence repulsion, basically, hence repulsion. And that's it. I don't think you would run out. Yeah, that's basically it. Perfect. Question 4. A transformer is used to provide a low voltage supply for 6 outdoor garden globes. The circuit is shown in figure 3. Assuming that there is no power loss in the connecting wires, all voltage values are in RMS values. Alright, so we can see basically we have a transformer, and no, this is cool. So what they've done is it's not in C, it's basically in parallel. It's a parallel circuit. Okay. The input of the transformer is connected to a power supply that provides an AC voltage of 240 volts. The globes in the circuit are designed to operate with an AC voltage of 12 volts. So pretty much each of these globes has to have 12 volts to pretty much operate correctly. So each globe is designed to operate with a power of 20 watts also. So each has to have 20 watts of power. Assuming that the transformer is ideal, so there's no power loss, calculate the ratio of the primary turns to the secondary turns of the transformer. All right. So you should know by Unit 1 physics how you would have done electricity, basically. So it's very important to still have that knowledge. Basically, if you have a parallel circuit, what do we know? So think about it. We need to provide 12 volts for each of these globes, and they are in parallel circuits. That tells me what? It basically tells me that we are, in the secondary circuit, there has to be 12 volts as an output. Like from the transformer, 12 volts out, because remember, in parallel circuits, what happens is that the voltage basically is going to be constant. So this will have 12 volts. This has so it doesn't half or break down. Like it doesn't equal. It's not going to like basically half or break down for each one of them. It's basically equal in so your voltage is equal in basically parallel circuit. So this is going to receive 12 volts, 12 volts, 12 volts, 12 volts. And so for that to happen, yeah, you have to have basically your output current, output voltage has to be 12 volts. So basically we have our, again, your input and your output, your secondary and your primary. So I need to get my, calculate the primary, number of primary to secondary turns. It's just equal to what? Your primary voltage to your secondary voltage. So what is our second primary? It's 242, 12, which is basically 20 to 1. Done. So basically we now know that's 20 to 1. Easy, basically. So we know, basically, let me tell you, basically voltage, when you're in the parallel circuits, it won't basically, each one of these little circuits will receive 12 volts. But it's different for, current. Current's actually going to break down. So, for example, let's say you provided, in this example, let's say you provided 60 amps. What's going to happen is 10's going to go here. It's going to half here. 10's going to go here. 10's going to go here. 10, 10, 10. So overall, the current that you've given 60, it's going to half. And when it comes back here, it's going to be back 6 amps. So, but can you see how it will half? Basically, it will equate. So you will try to equate in a parallel circuit. And yeah, so let's look at the next question. The globes are turned on. Calculate the current in the primary coil of the transformer. So we want the primary current in the primary coil. Well, all we're going to need to do is pretty much find the current in the, this circuit here. Now, well, like what we said, imagine that there's a current that was given here, basically. And it should be coming out the same. So, and remember how we said that it will always, not half, but like it will always try to equate all of its current to the circuit. We know the power basically for each globe is 20 watts. And we know the voltage they run. So if I know that P equals VI, basically, P equals VI, I can find the current in each of these parts of each of these circuits, little circuits. So current is just your power, which is 20 divided by your voltage, which was it 12? Yeah. So that's going to be 20 divided by 12, which is basically, each of these circuits is going to have 1.66 amps. So each of these circuits is basically running on 66. So that's going to have 1.66 amps. Basically, yeah, that's going to have 1.6, and we duplicate, that's going to also run. That's also going to run. That's also going to run. And basically, that's what's going to happen. And we know overall that these will all add up when they come out to what? Basically, how much are there? It was 1, 2, 3, 4, 5, 6. There's 6, so times it by 6. So guess what we've learned? Your actual current for you to produce this has to be on your secondary has to be 10 amps, basically. Because if this equates here, this will receive 1.6, this will receive 1.6, 1.6, 1.6, 1.6, and 1.6. When they all come back, it will bring back 10. So overall, yeah. So your actual secondary current has to be 10 in this question. I hope that makes sense. I know it's quite hard to understand a little bit of electronics. If you have done Unit 1 Electronics and Physics, you would know this basically. It's very easy. So, yeah. So we times that by 6, and so that's 10 amps. And now all we need to do is basically, we know that the voltage, the number of primary turns to your secondary is equal to your current to your secondary over your primary. So basically it's 20 to 1 is equal to your secondary is, what was our secondary to? It was 10 over IP. Basically your secondary is just 0.5 amps because it's half. So 10 divided by 20 basically, which is half. Yep, easy. That's how I would approach this. Next question. Explain why the input current to the primary coil of the transformer must be an AC rather than constant DC for light globes. Very nice, easy. We know that transformers only work for AC. Why? Because transformers, they work through the process of induction. And induction needs a change in flux, basically. For induction to work, you need to have a changing flux. You need to have a change in flux. And basically, why do we use AC? AC actually has a changing flux, whereas DC is just a constant flux. So remember, if it's constant, it's not changing, so you're basically doesn't work. It doesn't, induction doesn't work for DC. So yeah, very important basically to have AC. Transformers only work on AC, basically, voltage. So that's very, very important. So how would you get these two modules? Just basically what we said. So transformers require a change in flux to induct, basically, for induction. So induct from one circuit. So basically from one circuit to, let me see that. So to get from one circuit to the other for induction, so transformers require a change in flux to induct from one circuit to the other. So from one circuit to another. And AC voltage, so AC produces, basically just AC produces a change in flux. Changing flux. Whereas DC produces a constant flux. I don't think you have to be very detailed. Basically just that. We know that only transformers require, they need to have a change of flux to work. And so AC does have a change of flux, whereas DC has a constant flux, basically. That's it. Question 5. Figure 4a shows a single square loop of wire conducting wire placed just outside a constant uniform magnetic field B. The length of each side of the loop is 0.04, so okay, it's a rectangle. The magnetic field lines have a magnitude there and is directed out of the page. Over a time period of 0.5 seconds, the loop is moved at a constant speed from completely outside the magnetic field to completely inside the magnetic field. Alright. Calculate the average EMF produced in the loop as it moves from the position just outside the region of the field to the position completely within the area of the magnetic field. Show working out. Easy! So we know that for EMF to be produced, what do we know? It's number of turns. In this case, it's just a one loop. So no, we don't need that. So it's just change in flux over time. So what's our change in flux? We know change in flux is our area. What's our area? So it's just going to basically 0.040 times 0.040. That's our area times your magnetic field, which is 0.3 over your time. And how long does it take to go there? They told us that for the part 0.5 for your time period. Basically, so 0.04 time 0.040, 0.3, and 0.5. So that's going to produce an EMF of 9.6 times 10 to the negative 4 volts. Yep, so 1, 2, 3, 4. Yep, that's it. B. On the small square loop in figure 5, show the direction of the induced current as the loop moves into the area of the magnetic field. So basically, to get the induced current, all you do is Lenz's law. So we're going from, basically, there's an increase in flux because we're going from nowhere and we're going into a magnetic field. So there's an increase in flux. So basically, Lenz's law states that when there's an increase in flux in which direction, in this case, it's out the page, what Lenz's law states, there's gonna be a induced magnetic field that will oppose that change in flux, and so it will be in the opposite direction of the field line. So the induced magnetic field in this case will not be, basically, you know how this is out the page. There will be an induced magnetic field that will be into the page if there's an increase. If there's an increase in magnetic field, so we've got that. So using your right hand grip tool, make sure your thumb is into the page, and basically your fingers should be rotating clockwise. So in other words, this is how the current should basically be rotating. Easy. So 1 mark. Nice. Next question. Question 6. Kim and Charlie attempted to create a DC generator and have arranged the magnets along the axis, rotation of the wire loop JKL and M as shown in figure 6. They are having some trouble getting it to work. They rotate the loop in the direction of the arrow as shown in figure 6. It makes sense why it doesn't work, because when they're rotating, so have a look at this, when they're rotating, the field lines are pretty much passing like this, basically. And so when they're rotating, the plane is always parallel to the field lines. So the field lines are never actually passing through the loop. So there's no change of flux produced. So yeah, as much as I want to rotate it, it's not going to work. So yeah. Using physics concepts, explain why this orientation of the magnets will not generate an EMF. Basically what we just explained. So let me write that down. So the plane of the loop is parallel to the magnetic field lines. Even if they rotate, so if they rotate, the field lines will not pass through the loop. Hence, no change in flux will be created. Hence, no EMF. Basically, that's it. I think that's all you need for 2 marks. Basically, a very nice, easy question. B. Kim and Charlie decide to move the magnet so that the EMF is generated. On figure 6, draw the positions of the magnets to ensure that an EMF is generated. This is easy. You just need to rotate them here. Put them here. Basically. Let me draw it nicely. So, you just need to rotate these magnets here. It doesn't matter if it's, north or south. You just need to rotate them basically 90 degrees for them to be here. Just basically copy that right there. So now, as this rotates, the fields are actually going to pass through it, and so there's going to be induced of magnetic field. There is going to be a change in magnetic flux, and hence an EMF will be produced. So it says Kim and Charlie decide to move the magnets. On figure 6, draw the positions on the magnet to ensure that an EMF is generated. Basically, that's it. I mean, just draw, yeah. Why'd they have to put something to write on? That's what I'm confused. Basically, good. So question 7. 2 high voltage transmission lines span a distance of 260 kilometers between a power plant A and town B as shown in figure 6. Power plant A provides 350 watts of power. The potential difference at power plant A is 500 kilovolts. The current in the transmission lines has an RMS value of 700 amps, and the power loss in the transmission line is actually 20 megawatts. Oosh. Show using calculations that the total resistance of the 2 transmission lines is 41. All right. So what I'm going to do basically is just draw a full diagram, like a circuit, to represent this whole thing. So like what I always like to do in these, questions, I like to basically simplify this whole diagram. And so, of course, we have our resistor. Basically, this resistor means our transmission lines. And then, of course, we have our... I'm going to call this town B. I'm going to draw it as a globe. I like to draw them as globes, basically. And there we go. There it is. So we know basically what? Power plant. So the power plant A provides 350 megawatts. So 350 megawatts, basically. The potential difference at the power plant is also 500 kilovolts. 500 kilovolts. The current in the transmission line has an RMS value of 700 amps, so 700 amps. And the power loss in the transmission line is 20 megawatts. Basically. And that is it. So show using calculations that the total resistance on the transmission line is 41. Easy. We're given both the current and the power loss. You should realize that we know power loss is I squared over R. So if we want the total resistance, which basically is just power over I squared, that's going to give us our resistance. What's our power? It's 20 megawatts. So 20 times 10 to the power of 6 watts divided by current squared. So 700 squared. That's going to give me... That was going to give me 40.8, which is basically 41. So I'm going to write 41 ohms, basically. That's it. Easy. Next question. Town B needs a minimum of 480 kilovolts. Determine if that 480 kilovolts will be available for Town B. Okay, let me just copy this whole diagram and basically use this to answer that. I'm going to come down here and use this diagram again. Come on. Here it is. All right. So how much voltage is actually going to be given here? left out. So if this is providing 500 kilovolts, of course we're going to have a voltage used here. So let's find out how much that is. Basically, we know that also power is equal to voltage times current. So your voltage is just power over current, which is what? What's our power? So we know our power is 220 times 10 to the power of 6, so mega, divided by our current, which is 700. That's going to give us 20 times 10 to the power of 6, 700 divided by 700. Make sure you divide it by 1,000 to make sure it's in kilovolts, so we can easily see what's happening. So basically 28.57 kilovolts. That's how much it's being consumed here. Basically 28.57 kilovolts. And so basically, yeah, if we're providing the whole circuit with 500 kilovolts and this is using this much, this what's left out with this? It's basically 500 minus 28.57, which is 500 minus that. We're left out basically with 471.4, basically 3 kilovolts. Now, we need a minimum of 400, but we're basically given the town B this much, which is less than our 480. So there won't be enough power. So no, there won't be enough. There won't be enough voltage. There won't be enough voltage for town B. For town B. Easy. C. Explain what would happen if the electricity between power plant A and town B were to be transmitted at 50 kilowatts instead at that 500 kilovolts, assuming that the resistance of the transmission line is still 41. All right. So let's have a look at this. Copy this whole thing, duplicate, and bring it here. Let's really explain. So we're doing an explanation question. So let me put it down here. So what's happening is we're changing. So of course, this is going to be changing if you're going to change some stuff. So we know that that was 41 ohms. And so we're changing this one here to 50 kilovolts now, basically. And we're trying to see what's happening now. So between the power plant A and B. Okay, so remember power is, we're pretty much providing the same power, basically, for the power plant A. So don't forget about, it's the same power. So what's going to really happen? Wow, that's big problem, because we know that, remember, so we know that how much current, so basically when we started, it was how much was it? 700 amps. But if you now do the calculation, so we know how, so you know power is equal to voltage times current. So current is your power, which times 10 to the power 6 over 50 times 10 to the power of 3. What's that? So 350 times 10 to the power 6. 50 times 10 to the power of 8. It is 7,000. We went from 700 amps to 7,000 amps. So we got a times 10 of current. The current times by 10, which is a big no-no. Remember, when current increases, what happens? The power loss in this transmission line also increases very badly. It's squared. So if we basically that's, you know, if your current basically times by 10, your power loss basically, because you just square it, it's going to be 100 times basically. So what's going to happen is in that the transmission, there's going to be a lot of power loss, 100 times the original amount if you're going to do that. And so overall, what's going to happen, if there's a lot of power loss here, there won't be enough power for town pretty much B. And so it won't run properly. It's even worse to actually lower that voltage. That's a big no-no. So that's what we're basically going to explain. Yeah, for 2 marks. I mean, you don't need to write a lot, basically. Yeah, so that's a nice diagram to help us. So all right, so let's say for the same power, but with low voltage, but with low voltage for power plant A, this will 10 times the current from basically 700 to 7,000 amps. This will create a large power loss. Basically, times by 100 in the transmission lines. Due to, of course, write the formula, P equals I squared over R. Hence, little power will be received to town B, basically. And that's it, basically. That is it. Easy. Question 8. Maya is at a skate park. She stands on her skateboard as it rolls in a straight line down a gentle slope at a constant speed. Constant speed, basically, whenever you see that word, it means your net force is 0. And acceleration also is 0. Whenever you hear constant speed in these times questions, the slope is 5 degrees into the horizontal. The combined mass of Mia is 65. In figure 9, sorry, my Siri is basically talking to me, which is, yeah. Alright. In figure 9, the combined system of Mia and the skateboard is modeled as a small box with a point M at the center of mass. Draw and label arrows to represent each of the forces acting on the system, that is Mia and the skateboard, as they roll down the slope. Easy. So basically, of course, there's a force of gravity that's going to be acting down, horizontally down, so force of gravity. Of course, we're going to have a normal reaction force that will be perpendicular to the slope, N. And do we have friction? Yeah, we do. The word here is giving you the hint, constant speed. Constant speed that the net forces are going to be basically equal. They're going to cancel out. So think about it. If I break this down to two components, these here will cancel out, but this force would be left out if there was no frictional force. And so we will have acceleration. So we have to have basically a force of friction. So because now when you basically add this part here and this part, they're going to cancel out. And so that's when you have no net force. So I'm going to cancel it. Basically, these are your forces. Done. B. Calculate the magnitude of the total frictional forces acting on me and the skateboard. Easy. Like what we said. So basically, break this down. I'm going to basically duplicate this here. I'm going to rub this part here. Alright, so we're going to have, of course, this angle here is going to be basically 5 degrees. That's your force of gravity. And so we want to calculate this part here, which is the one that's making it. Basically, the things that are not accelerating, there is no acceleration, but the net force is basically, we know that F net, which is 0. F net is the total sum of this force and this force. So it's going to be basically the force of gravity sine 5 degrees minus your force of friction. And we know F net's 0, like we said. So Fg sine 5 degrees minus your force of friction. So your force of friction is basically Fg. What's Fg? It's the mass times your g. So 65 times 9.8 sine 5 degrees. That's going to give me 65 times 9. So 65 times 9.8 times sine 5. That's going to give me basically 56. 56. Easy. Near the bottom of the ramp, Mia takes hold of a large pole and comes to a complete rest while still standing on the skateboard. Mia and the skateboard now have no momentum and kinetic energy. So explain what happened to both the momentum and the kinetic energy of Mia and the skateboard. No calculations required. All right. Okay, wait. So when it talks to momentum, I see a very similar kind of question that came up in the 2017 VCA Northern Hemisphere exam, basically. I think it a little bit tricked a lot of questions in that exam. So this question here, I think it will also trip a lot of students who didn't do some past papers. So momentum. All right, let's think about momentum. So if she has a lot of momentum, remember, she's like, she's coming, she has momentum with her. And so as she pretty much, remember, momentum is not lost, but it's transferred. So when she basically collides and holds this thing, momentum's basically going to be given to the large port, and the large port's going to give that momentum to the, basically, Earth itself. That's where the momentum actually went. It's gone to the ground, the Earth, basically. So a lot of students maybe don't know that, but remember, this question came up in the VCA 2021 Northern Hemisphere. I'm telling you guys, make sure you do all your practice exams. Do all of the VCA ones. I'm telling you, because they repeat. Those questions always repeat. So this question, I believe, if I'm looking, I'll probably look at the, the report and probably see that a lot of students got it wrong, because they don't realize that, yes, momentum is transferred to the port, and so it would probably it always goes down to the Earth, basically. So basically we'll say, let me write it nice down. Momentum is transferred to the Earth through the pole, basically. Through the pole. And so let's talk about also kinetic energy. Now, of course, she has kinetic energy, but when she grips this, what happens? There's so many forces. I'm not going to lie. There's sound. Like, when she hits it, it's like ding. So some of the energy would have went to sound. Some of the energy went to heat. So when she's holding that grip, she has friction on her hand, which is basically heat. There's also, when you're holding that grip, she's using her muscles, I think. So if you're using your muscles, your muscles are doing work. So that's also energy, which is work that your muscles are doing. So basically, any of these, I think, should give you the mark. I mean, heat, sound, work, and the muscles. But yeah. So I'm going to just say kinetic energy is transformed to, basically, let's say muscle, to muscles doing work, or like heat and sound. Any of these, basically, doesn't matter. So yeah, easy. And that's it. Question 9. I think the question 9 is the last question. Let's smash through this. Yep, all right. Question 9. Georgos is practicing, I'm going to call him George, basically, just to, destroy his name. George is practicing his tennis serve using a tennis ball of 56 grams. George practices throwing the ball vertically upwards. So, okay, from point A, so from basically this point here to point B, as shown in figure 10. His daughter Eka, a physics student, models the throw, assuming that the ball is at a level of George's shoulder, point A, when it leaves his hand, and also when he catches it again. So, okay, point A is 1.6, basically 1.6 meters from the ground. The ball reaches the maximum height at point B, all right, 1.8 meters above George's hand. Show that the ball is in the air for 1.2 seconds for the time it leaves George's hand, and which is level with his shoulder until he catches it again. So basically, he's going to throw it, and it's going to go to the maximum height and come back, basically. So all we need to basically find is how long does it take for him to throw the ball to the maximum height. So what's the time? And double it, because it's going to take the same time to go down, basically. This is basic vertical motion, which you would have learned in Unit 2 of physics. So let's do that. So we know basically he's going to have, when he throws it, we know that the final velocity has to be 0 at the top, your vertical velocity. Of course, acceleration is negative 9.8. S is your displacement is going to be 1.8. And it's going to be positive. So, and we want to find the time. So we know that the formula should be S is equal to VT minus half AT squared, which is 1.8. That's going to be negative half, negative 9.8 T squared, Basically, T is what? 1 point, so 0.5, 9.8, 1.8, answer. And then you take the square root of that. That's going to be 0.60 or 0.61 in this case. I'm just going to 0 actually, yeah. So 0.60, and then you just, that's how long it takes to go basically from here to here to be. And of course we double it because that's how long it takes to go back down. So hence your time is basically 1.2. Easy. George swings his racket from point D, okay, through point C, which is horizontally behind him at the shoulder height as shown in figure 11, to point B, all right. Eka models his swing as circular motion of racket head, all right. So the center of the racket head moves with a constant speed in a circular arc of radius 1.8 meters from point C here to point B, basically. Basically like this. This is going to be like a nice circular arc. All right. So the racket passes point C at the same time that the ball is released to point A. Okay. And then the racket is hit the ball at point B. Beautiful. So what happens is basically when the racket's at point C, so imagine he starts at D. So the racket's hitting, coming. When it reaches point C, basically, the person, George, he throws the ball with it now. So at this position, he throws the ball. So the ball goes up. When it reaches up, it's basically the time it takes for him to hit the ball, which is, so overall, you know how we found out that the time it took to go up to this position from A to B was 0.6 second, basically? It's the same time as it takes him to basically go from point C to B, because that's where he hits it, basically. And what we're trying to do is calculate the speed of the racket at point C. Easy, because basically it's going to be the same here, because it's basically constant speed. We just need to calculate, because we know the time it takes to go from here to here. We just need to calculate basically the length of this, or quarter of a circle, this length here. Basically, we know that the circumference of the circle is 2 pi r. And it's actually a quarter of a circle, so I'm going to divide it by 4. That's going to be pi r over 2, basically. So what's that? So pi, your radius, they told us the radius, 1.8, 2, basically, pi times 1.8 divided by 2, basically 2.827 meters. Done. So if we got the distance, we know that speed, so speed is just what? It's the distance over time. So we know it's 2.827 divided by that time, which is 0.6. Which is 4.7, basically. That's the actual velocity that they hit it. Beautiful. C. The ball leaves George's racket with an initial speed of 25 meters per second in a horizontal direction. So, as shown in figure 12, a tennis net is located 12 meters in front of George and has a height of 0.9. Alright, so this looks like projectile motion. So, how far above the net will the ball be when it passes above the net Y? Assume that there's no air resistance. Show you working out. 3 marks. Wow. So basically, 100% this is going to go for projectile motion, so it's going to go like that, and it's probably going to maybe be in this position when it, or like, you basically know it's going to be like that. But all we need is just when it hits, it goes down, around here, where, and we know what we want to basically do is we want to calculate distance, this distance here. I'm going to call it Y. Basically, that's the distance above the racket and where it is. That's what we're trying to calculate. How far above the net will the ball be passing above the net? So, all right. We're given that horizontal velocity, and we're also given the horizontal displacement. What do we know? We know because the horizontal velocity is constant. We know how we can easily calculate time because we know that distance is voltage. What am I saying? Voltage, velocity times time. So your time it takes is your distance, which is 12, over your velocity, which is 24, which is 0.5 seconds. It basically takes 0.5 seconds to go from here to here. Done. We've got the first point. And now what I'm going to do is I'm going to use vertical I'm going to use, I'm going to calculate the vertical displacement, because the vertical displacement will give me basically this over here. It'll give me this over here. This distance, basically. So I'm going to do that. So I know the initial vertical displacement is u equals 0, basically. A is going to be negative 9.8. And we know the time it takes is 0.5 as we calculated it. So your S is what? So we know it's going to be basically S is equal to UT plus half AT squared. So S is basically half negative 9.8 T squared, which is 0.5 squared, which is negative 1.225 meters. It makes sense why it's negative, because it's going down. So this basically distance here is 1.225 meters. And yeah, now basically all we got to do is just equate, because have a look at this. We know basic mathematics here. So we know that adding all these up, so like this, that should equal to these two added, like to these two added. So because that distance here is equal to that distance here, basically, and we can easily calculate then y. So basically, what's y plus 1.225? So 1.225 plus 0.9, which is 2.125, should equal to, what's 1.8 times 2, pretty much? 3.6. So y is basically 2.125. It's basically 1.4475, which is basically 1.5 meters. And that is it. I hope you guys enjoyed this video and learned something through this video. I hope it makes a lot of sense, like it, made you a little bit become better in physics. Thank you guys for watching this video. Please make sure to like and subscribe, and for more future videos. And yeah, guys, if you have any questions, make sure you put them in the description below or in the comments. And I hope you guys have a great day, and make sure you take care of yourselves. Bye bye.